Hey guys, in this video we're going to talk about a topic called dielectric breakdown, which opens with the question, how much charge can you put on a capacitor? Now, first thing is I want to actually show you a couple of capacitors. This one here is a 1 farad capacitor. Holy cow. And notice it says, it's a little, why is this so, it says on it 5.5 volts. Alright, that means if you put more than 5.5 volts on this thing, it's going to break, maybe explode. This one, however, the limit is 50 volts. Now, I realize that volts and charge aren't exactly the same thing, right? So it's two different ways, though, of saying what the limit is, since after all, capacitance is charge divided by voltage. Alright, so that means that if there's a maximum voltage, there's also a maximum charge, which is based on that maximum voltage. Okay, so fine, whatever. There is a maximum charge. So the question then is, why is there a maximum? Why can't I just keep adding more and more and more? Well, the answer is related to stuff that you've seen in everyday life. For example, stop me when you know what I'm drawing here. Lightning. Lightning is related to the reason why there's a maximum amount of charge that you can put on a capacitor. So here's a crazy idea. We said capacitors are basically, like you got a parallel plate, you put a certain amount of charge on one plate, certain amount of charge on the other one, and there you go. Now it's a capacitor because you got two parallel plates. Well, a cloud isn't exactly that, but effectively you can treat it like it is because the ground is one plate and the cloud itself is the other one. And so, at a certain point, there will be so much charge built up on the cloud that you get this phenomenon called dielectric breakdown. Let me write this awesome word for you. So, dielectric breakdown, what is that exactly? Well, dielectric breakdown is sparks. It's that phenomenon where you will see charge jumping from place to place. Whoops, a little cut off. So lightning is the most fantastic example of it. But if you've ever seen something like when you say rip apart a fuzzy blanket from a cotton sheet, and there's like this 3-inch long spark, that 3-inch long spark is dielectric breakdown. Or you stand up off of the fuzzy couch, you are now charged, and then you go and you poke something, and then there's a bazap, right? That little bazap is dielectric breakdown. Okay, so fine, that's what it is. It's the spark. It's charge jumping from place to place, just like this cloud to the ground, right? Charge is jumping from one place to the other. And the same thing will happen inside of your capacitor. And when it happens inside of your capacitor, it breaks the capacitor, right? If you've got charge jumping between the plates, that's going to generate heat, and then it's going to go kaboom. Alright, so that's what dielectric breakdown is those sparks, but the question is, why does it occur? Well, the reason it occurs is because there is a limit on the value that the electric field can be in between the two plates of your capacitor. Now, what that value is depends on what exactly the dielectric is, because, if you have a great dielectric, then this is going to be a huge value. But if you've got a crappy dielectric, then it'll be some small, dinky little value. Air, it turns out, is a reasonably good dielectric in terms of having a large, what's called dielectric strength, which is this. So for air, 3 times 10 to the 6th newtons per coulomb is what's called the dielectric strength of air. But that's really just a fancy phrase for the maximum electric field, okay? That's really all that actually means, okay? So now, I want you to make sure that you do not get that confused with one other term, which also has the word dielectric in it, confusingly, and that is dielectric constant. All right, now I want you to think back to the previous set of lectures in which I talked about the dielectric constant. What was the dielectric constant? What symbol was that? You don't remember? Oh, you're supposed to remember this, guys. Oh, good, good. I'm glad you are pausing the video and looking back at your notes. Yes, that's right. It is the letter kappa. Not, oh, that's cut off. Let's try that again. Not K, mind you, but kappa. Okay? Because if you say that it is K, then you might get confused with other things that actually are K. So the letter kappa is your dielectric constant, not your dielectric strength. Okay? Something can have a large dielectric constant without having a large dielectric strength, right? So they're unrelated quantities, all right? Dielectric strength, on the other hand, is, since it's E max, the maximum electric field, it is E. Now, E stands for electric field. We so far haven't learned any equations that have the letter E in them. So at this point, what I will do is introduce you to two additional equations that are going to have electric field in it and allow you to relate dielectric strength to charge and voltage. All right, on the left we have the new equations. Ooh. All right. On the right, we have the old equations that you're already supposed to know, but we'll talk about how you put those two together. So bear in mind, E is not always the dielectric strength. It's just what is the electric field. All right. So you can now calculate the electric field between the plates of a capacitor, right? Which, if you were wondering, what? I don't recall mentioning this before. No, we didn't. We kind of didn't talk about it in the last lesson, but yeah, there's an electric field in between the plates, right? You got positive on this side, negative on this side, so you can bet that if you put, I don't know, a positive charge in between, it would be very strongly pushed in one direction, right? Negative would, of course, be pushed in the opposite direction. So there is very definitely an electric field in between the plates that points from plus to minus. All right, now the equations on the left side could be used to calculate electric field for a variety of circumstances, and which one you would use would depend on what information you had, and also your own sense of convenience. Like this equation, I love it. It's so easy. This equation is not my favorite because it's annoying. So fine. This one you could use, but really my general tendency is use this one if at all possible. Now, this one relates electric field and voltage. If they're asking a question about charge, then you might be stuck using this one, unless you can get away with finding the voltage and then plugging it into this one over here to find the charge, which might work, okay? It just depends on exactly what information you have or don't have, which of those equations you are able to use. Now, we said E doesn't have to be the dielectric strength, but if you have a problem which is about dielectric breakdown, then there it is. That's where you will plug in the dielectric strength. Okay? So it is the electric field in general, but specifically, if it's a dielectric breakdown problem, then it's the dielectric strength. All right, now, Mr. Errico, how do I know that they are expecting me to plug in the dielectric strength? There's a key word or two that they're looking for. So one would be if they exactly say breakdown, fine. I will usually not use that phrase. If they say breakdown, so be it. But more often it'll be maximum. All right, if they say calculate the maximum charge or calculate the maximum voltage, then you're going to use the dielectric strength and plug it in for the electric field in one of those two equations. Now, this is example 2 I'm going to take a look at. I'm not writing all of the text. Have your packet in front of you. If I wrote all the text, it would take up all the space on the screen. So it wants to know the maximum volts, right? The volts needed to produce dielectric breakdown if our plates are separated by 3 centimeters versus 1 centimeter. All right, now the equation we're going to use for this is delta V equals ED, or sorry, V equals ED is the way I'm doing it for this video. So we're trying to solve for V, the number of volts, but there's something funny going on up here with these units here. I just told you in the previous segment that it was newtons per coulomb, and here I am saying volts per meter. What's up with that? Well, what's up with that is it turns out that a newton per coulomb is a volt per meter. Now, there's a couple of ways to show that, but the simplest one is I'm just going to reference this equation right here that I just wrote down. If I solve this equation for E, then I'm going to get that it is V over D. Well, V is volts. That's measured in, oh, let me think now. Oh, it's volts. And distance, the plate separation, which is what that D is measured in meters. So there you go. An electric field is either newtons per coulomb or volts per meter. Either one is going to work. Okay, so 3 times 10 to the 6 volts per meter if I want to know the maximum volts that can be put across 3 centimeters, meaning before we get dielectric breakdown, I'm going to put in 3 times 10 to the 6th for E, because that's the dielectric strength, and 3 centimeters for my plate separation. Now be careful here, you have to put it into meters. So this result is going to give me 90,000, I think. Please forgive me if I screwed up the place value, but 90,000 volts. Well, that is sure a lot of volts. It's going to take a lot to break down that much. Now, just to make sure everybody understands this unit a little bit better with volts per meter, if it's 3 million volts per meter, that means that if my hands were a meter apart, nowhere near that in this video, but if they were a meter apart, it would take 3 million volts to make a spark a meter long. Think about what that means for lightning. A lightning bolt is like a kilometer long. So that's 1,000 meters. That's 3 billion volts to break down a kilometer of air. That is a lot of volts. Okay, now part B of this question, all we'd really need to do differently with this one is plug in, there. Now it says 1 millimeter, 0.001, and that will change the value to only 3,000 volts. Alright, so it's much easier to cause a spark that's a millimeter long. You've done that plenty of times, anytime you've done dielectric breakdown with your finger touching a charged object. Or, excuse me, after being charged from standing up off the couch and doing triboelectrification and all that. Alright, here we are in example 3, trying to find the capacitance of a capacitor made with 2 aluminum foil strips like this, a piece of paper in between them with a dielectric constant of 2. Okay, so to find the capacitance, we will reference one of our old equations and go with kappa equals epsilon naught A over D. Okay, and then all we got to do really is plug in here, being careful with the units. Okay, so pause the video and you try and figure out what is the capacitance based on what's been described. This is not new. This should be a review from the previous lesson. So pause me, go. And here we are with the answer. I think probably the trickiest part here is the units. Whoop, hey, where'd that thing go? Oh. All right, that would be the plate separation here, which was 0.1 millimeters. Okay, so a bunch of leading zeros. And then you got to make sure you put the area in the right units. Convert first. Now, if you're saying to yourself, Mr. Erica, what about the 14 times 10 to the 6th number? I didn't use that. You're right. You don't need it. You don't need it until part B, where it asks you for the maximum potential and charge. So let's give that one a shot. Now, at this point, since I'm starting to run short on time, what you should probably do is just pause the video periodically and check my work and see if it's correct. Also, when we get to part C, I have a new equation to introduce, and I'll write that down. But yeah, just pause and check the work. There it is, 1,400 volts. See if you can figure out how to use that in C equals Q over V so that we don't have to use that other awful equation I showed you. There's that, and oh, I guess I didn't give you an answer. Well, alright, and there's that. Alright, next is part C. Alright, here's the equation for energy, or rather the 3 equations. This one, so there's not a lot to understand here, it's mostly just plug and chug. So this is the basic equation, but you don't always know both charge and voltage, so that's why there's 2 other forms for it. If you imagine taking this equation and, say, solving it for charge, since Q is C times V, well then if I replace a Q with a CV times another V, then I would have this one, 1/2 CV squared. If I did it the other way around and solved for V and plugged in, then I would get this 3rd equation over here. So you can really use any of those that you like. Okay, now, knowing that that's the equation, go ahead and calculate the energy with whichever one you want. Alright, there it is, and if you did any of those 3 equations, you should get that same exact numerical value. I just happen to pick this one. I don't know, I just like it, but any of them will work. Alright, leave me a comment and let me know how I did.